Hey, everybody.
Hi, Dr. Tran.
How's it going?
Good. How about yourself?
Good, good.
Last day of the semester.
Last
Crazy.
day. Yep. All right, it's 5:30, so let's go ahead and get started. All right, so for the last time this semester, good evening, everyone. How's everyone doing today?
Doing well. How are you?
Good, good. Yeah, it's excited for the last day, but also kind of sad at the same time too. You know, it's like we've reached the end of a long journey. Okay, good, good. All right, and so the plan for class today. Actually, I'll be honest, I didn't have a plan for class today. This last week was kind of just meant to just kind of catch up on stuff, maybe have some guest speakers. So we had Adam present on Tuesday, and I apologize again, for not recording that session because Adam talked about a lot of great stuff, but unfortunately I dumb me, I forgot to hit record on the screen. So that's my bad. So I apologize for that, but he did leave us his email, and for those of you who are interested in reaching out to learn more about what HeartFlow does or anything like that, hopefully you can reach out to him. And yeah, for those of you who are just coming from 410, the presentation given by Walid and Salman, who work with ANSYS a lot, was awesome. Yeah, that was really cool to see all the different kinds of applications. Yeah, at one point Josh messaged me and he asked if you were in 442 when Salman was talking about the stent deployment and stuff like that. So yeah, that was awesome. Okay. So I did want to mention that I did finish grading the midterms, as probably you guys noticed last night. So those scores are up. I believe the average was around a 40 out of 50, and so the average was about 80%. So that was it was good. Okay. And the solutions are up on Canvas as well. And so if you go on the Canvas site, actually let me go show you right now. Okay. So you go under Files, you go under Solutions, and you can see the the midterm 2 solutions are here. Okay, and so definitely check those out. Check out the feedback that I gave you, and any mistakes that I made. Of course, you can let me know. And I'm always happy to look at exams again. Mm-hmm. Right. Do I grade those, or do one of my minions do it? I wish I had minions, but I have no minions. So the only minion is myself. So I did all the grading for that stuff. Yeah. Mm-hmm. Okay. So before we start today, I don't think we've talked about it in this class yet, but as you probably a lot of you guys have done this already, but SOQs are up. Okay, so SOQ stands for those student opinion questionnaires, and so probably you guys have done this dozens of times at this point, but that's your guys' chance to kind of tell me how this class went for you. Okay, and for this class, that's especially important because as all of you know that this is a brand new class. And so this is something that I'm trying for the very first time. And so I tried a lot of really new stuff in this class, a lot of things that, I just honestly just wasn't sure how it was going to turn out. And so I know in a lot of sense, this class was kind of a bumpy road in a lot of ways. And so I really want to hear from you guys, to hear how the class went for you, because, I'm hoping that this is something that's going to be, that I want to add to the permanent curriculum. And so right now this class it's not part of the full curriculum. It's technically just, it's called a special course, right? And so you'll still get credit for it. And so, you'll still get, the graduate credit, technical elective credit, all that stuff. I just talked to the advisor this morning, and so she told me, Dr. Weiss told me that it's all good. But, before a class, gets added to the full curriculum, it has to go through another round of reviews. And a big part of that is your guys' evaluations, right? And so, typically I think a special course is offered about 2 or 3 times before it gets added, because, the general understanding is that the first time you offer the class, it's probably not going to go that well, because, you're trying a lot of new things, and, things just aren't going to go over right. And so, I really want to hear from you guys about how this class went, because, that's important feedback for me to improve this class for the future. Okay. And I think this class is especially unique too. This class is especially unique too, because I think it's quite different from a lot of the other classes in a lot of different ways, and that a lot of the methods that we're talking about, I think are kind of just starting to be adopted by the industry, right? And so Adam talked to you guys a lot about what HeartFlow does on Tuesday, but they're pretty unique. And so there a lot of companies out there, a lot of engineering biotech companies still haven't really moved into the simulation space all that much. And so that's different, because usually, when you take a class at college, it's usually lagging behind the industry a little bit. And so this class, I'm trying to give you guys kind of a little sneak peek into what possibly the future could be. And so, I think, from that perspective, it's pretty exciting. But, at the same time, because a lot of these methods are still being formed and a lot of them are still being developed, just naturally, it's going to be a little bit more messy than something like your typical heat transfer, typical fluids class. Yeah. And so, yeah, so definitely fill those out. Just be on. One thing I always tell my students is just be honest with those evaluations, right? And so there's nothing worse than, in a lot of ways, there's nothing worse than someone that just tells you don't change anything for the class, right? Because that's not helpful. Because what's helpful is hearing, here's my experience with the class and here's how I think it could be improved. And so if someone just gives you a high five and just tells you great job, like that's not. It's nice, but it's not super useful if your goal is to kind of improve the class. And so please, fill that out, be honest, and just tell me how you really feel. Okay. Okay. And so that's out of the way. Okay. Okay, and then so the plan for today. And so today, I honestly, I reached to this point in the class, and I realized that there wasn't really much I had prepped. And so, I'll give you guys a choice. And so originally, I was thinking that maybe we just take a day off today and then just we'll just end the semester a little early. But I thought another cool thing that we can do is we can talk about some of the simulation features within SimVascular that we haven't really had a chance to talk about yet. And so what you guys are doing for your projects is just a steady simulation with deformable walls, with rigid walls, sorry. But there's a lot more that's in SimVascular that's out there. So in terms of, mostly in terms of the boundary conditions, for the inlets and outlets, and also the deformable walls. And so I thought one thing we can do today is we can go over some of that stuff, and just kind of show you guys what the capabilities are, and we can go from there. Okay. Pizza party, I wish. Yeah, if we were in person, I could order pizza, but if I order delivery pizza to all your guys' houses, then I think that's my entire paycheck for the month. So so I can't do that. But if we were in person, we could have a pizza party. But unfortunately, we're all in our homes, so we can't do that. So I'm seeing some votes to go ahead with the simulation stuff. So I'll go ahead and do that. Okay. And if you want to apply some of the stuff we learned today to your final project, I would say go for it, but none of that is required. Okay. And so, because I know it's already been quite an ordeal just to get the geometry up and going and to run just the basic simulation. And so that's all I'm going to require for the project. But in case you were wondering what other tools are out there for simulations, then we can go over that today. Okay, and so let's go ahead and start that then, right? And so to help me, and just to kind of simplify things, I have a model here of what we call an idealized blood vessel, or otherwise, what 99% of the world calls it just a tube. Okay, and so a tube is very nice in these kinds of in my world, because it's kind of the simplest geometry that you can do to run a simulation on. And so all the testing and all the code development is usually done on cylinders, because that's kind of the simplest thing that you can do. Okay. All right. And so let's go ahead and let me show you the, and so, you can see the model here. Okay. And you can see here, I have several different simulation jobs done. Okay. All right. And so the first one is just a steady simulation. And so this is kind of the vanilla simulation that you guys are all running in your, for your projects. Okay. And so that's all good. And so first thing I want to show you guys is how to run an unsteady simulation, okay? Because we've spent a lot of time in this class talking about blood flow is pulsatile in nature, and so it's unsteady. And so in a lot of sense, the simulation you guys are running for the project doesn't really capture that at all, because you're assuming that basically the flow at your inlet is not changing with time, okay? And so in your simulations, you can actually do an unsteady simulation where you apply a pulsatile inlet. Okay, and let me show you how to do that. And so it's actually pretty simple. Okay, and so the big thing that you have to change here is you have to change how you prescribe the inlet condition. Right? All right, so let's go ahead and take this from the top. And so let me go ahead and create a new simulation job. Okay, and so I'll call this unsteady. Okay. And now we're in the simulation framework. Okay. All right, and so I'm going to run through a lot of these pretty quickly because I know a lot of you guys have been doing this for your project already. But for basic parameters, we're going to keep all of these the same. Okay. Next, we come to the inlet and outlet boundary conditions. Okay. For the outlet boundary conditions, I'm going to keep it as a resistance. Okay. And I'm going to keep the same resistance value that I have for the steady here. Okay. And for the inflow, we're going to have a prescribed velocity. Okay. And here's where things change. Okay. All right. And so when setting up your prescribed velocity boundary condition, all of this is the same as before. Okay. And at this point, what I had you guys do was I had you load in a text file called steady.txt, right? And so, it might look something like this, right? And so your steady.txt usually has, just two entries in it, right? And so it has a time value of 0, and then a flow of -100, and then a time value of 1 and a flow value of -100. Okay, and so this basically tells the simulation that we want our inflow to be 100 milliliters per second, and we want it to stay it that way for the rest of the simulation. Okay, and so that's fine if you want to run a steady simulation. But what if you want to run an unsteady simulation where the flow actually changes with time? Okay, and so the way that you do that is you apply a different text file here, which has describes your flow waveform. Okay, and so this is something that typically you prepare yourself, right? And so you either obtain a text file like this from from someone who's done it before, or more commonly, if you have measurements from inside the patient. So let's say that you ran like an ultrasound, and you were able to get a tracing of their flow over time, then you can apply this as their boundary condition as well. Okay. And so to kind of show you what this looks like, because right now we're kind of just looking at a two lists of numbers. Let me copy this into a spreadsheet so you can kind of see. Okay. All right, and so I've listed these into a spreadsheet, and so we can go to Insert. Let me do a scatter plot. Okay, and you can see here that this is the flow waveform that we're going to apply, right? And so I think this waveform actually was taken from a measurement inside a patient. And so what we have here is that for the beginning stage of this flow waveform, what we have is the heart is contracting. Okay, and so as the heart contracts, it's going to eject a lot of flow into the aorta, right? And then when the heart is relaxing, what you have is kind of very low flow over here. Okay, and then if you extrapolate, then you can kind of see that this waveform is right at the end here, is starting to contract again, and we're going to have another big peak right here, just like that. Okay, so we have right here a pulsatile waveform, but we only have just one cycle of this, and so this is just one period of our waveform. Okay, and so we're going to apply this instead as a inflow waveform for our simulation. Okay, and so when we come over here, okay, and we are asked to find the flow rate for the file. Okay, let me navigate to that. Okay. All right, and then here we've loaded in that that file. Okay, and then now we can put in a period as well. Right. All right, and so the period here it's usually set to be whatever the last time step in your flow file is, and so usually that's set automatically, but you can change that if you want. Right. All right, question. So is that what the periodic time reference in the data sheets is for? Yes. Yes, and so probably in your data sheets you probably had references for what the heart rate was, or what the period of the heart cycle is, and so that's what this is, and so that's basically how long it takes for that waveform to kind of repeat itself. Okay. And so here I have a generic one that I showed you. So the generic one just has a period of 1, which is not bad, because a period of 1 basically means your heart is beating 60 times per minute, and so that's relatively healthy, but but it's realistic. Okay. And so it is possible for people to have a heart rate of 60 beats per minute. Right? And in fact, actually, if that's your resting heartbeat, then you're probably in pretty decent shape. Okay. All right. And so at this point, we can kind of explain what some of these other parameters do, because I think when we first ran our vascular tutorial for simulations, we kind of just glazed over these. I said just leave them alone and don't touch it, right? But now we can actually see what they're used for. Okay. And so let's first talk about the Fourier modes. Okay. And so if you remember, a few weeks ago, we talked about the Wolmersley solution, right? And so from there, we kind of did a little bit of a review of the Fourier series, okay? And remember what the Fourier series says is that, you can take any periodic waveform and you can replicate it with the sum of sines and cosines, right? And so, that sum there is an infinite sum, right? And so you have an infinite sum of infinitely many sines and cosines, and with that you can replicate any waveform, right? But realistically, you're not going to have time to do an infinite summation, right? And so you don't have enough time to sum an infinite terms next to each other, okay? And so usually we truncate this, or we cut it off at some frequency. And so this Fourier modes right here gives you kind of a control over how many modes that you want to include, right? Or how many terms in the Fourier series that you want to include to approximate your waveform, okay? And so 10 is usually pretty good. And so for 10, that usually gives you a pretty good amount of accuracy, but it also kind of helps smooth out your curve a little bit as well, okay? For this particular file, that's not really necessary because the curve is already pretty smooth. But a lot of times, if you're taking in measurements directly from a patient, you might have a lot of signal noise that might be there. Okay, and so this kind of helps smooth out some of that signal noise so that you don't get that stuff in your simulations. Okay, and then the point number here, that just is just another thing where it kind of helps approximate your waveform, and that's basically how many time points that you want to have per cycle to approximate your waveform. Okay, and so it's something around 100 to 200 here is also pretty good. Okay. Because a lot of times, what you want to do is because if we look at this file again, okay, it's a little bit hard to tell from here, but what we have is basically 1,000 data points in between time 0 and time 1. Okay, and so a lot of times that's a little bit of overkill in how many time points that you need to actually simulate the job. And so a lot of times we call this subsampling, and so we only take a subset of the samples in order to reconstruct our waveform. Okay, and so this number basically specifies that, and so usually 200 is plenty, and it usually gives you pretty good accuracy too. Okay, all right, and so that's the main difference for pulsatile, right? At least for setting the boundary conditions. There's a few more things that we have to change, but are there any questions at this point? Okay, all right, and so let's go ahead and hit OK. Okay, and so now our inlet profile was prescribed. Okay, for the wall properties, we're going to keep it as rigid. Okay, and so that's not going to change. Okay, all right, and so now let's go to the solver parameters. Okay, and so here's probably where the main difference is. Okay, all right, and so when you run an unsteady simulation like this, what's going to happen is that the flow rate is going to go up and it's going to go down and it's going to go up and down like that. Okay. And so here, when you select the number of time steps, this is a lot more important than your steady simulations, okay? Because in your steady simulations, I basically just have you guys run this for 100 time steps. And for steady, that's fine, because all we want to do for steady simulations is we want to simulate until we reach steady state, okay? But for unsteady simulations, it's a bit different because we never reach steady state because the conditions are always changing, okay? And so now our goal with the number of time steps is going to change a little bit. And so what we want to do with the number of time steps here is we want to make sure that we simulate an adequate number of cycles. Okay, and so now we need to think about how many cycles are we simulating with our simulation. Okay, and so if we go back to the inlet and outlet boundary conditions, we know that our inlet waveform here has a time period of 1. Okay, and so it's going to take 1 second in order for that waveform to fully, do its thing. Okay. And so at the very least, we want to make sure that we simulate that entire cycle, right? And so we don't want to cut the simulation off early, right? And so let's say that if we do our typical thing where we set the time step size to 1 millisecond, okay? And we only simulate it for 100 seconds or for 100 time steps, right? Then we're only going to be simulating this for 0.1 seconds, right? And so if we go back to our flow waveform, right? This means that we're only simulating it up to here, right? And so we're only simulating it for these time steps, right? All of these times here, we never simulate just because we cut off the simulation too soon, okay? And so you want to make sure that you specify a number of time steps here that's at least 1 cycle, right? Because otherwise you're gonna miss everything else, right? Okay. And so for this case, we want to make sure we simulate for at least 1 second. And so for that, we have to have a number, we have to have 1,000 time steps and a time step size of 0.001. Okay. Okay. But it goes beyond that. Okay. And so, getting one cycle is that's the bare minimum. But what can happen sometimes in these simulations is that it takes several cycles in order for the simulation to kind of what I call warm up. Okay. Because if you imagine, before we start the simulation, we're basically starting from rest, right? And so all the fluid inside this tube is not moving, okay? And then all of a sudden we're applying this kind of pulsatile waveform to it, okay? And so, it takes a while for the inertia inside the tube to kind of realize, what's going on, right? And so, if you can imagine that at the beginning, all the fluid in here is just chilling, and then all of a sudden it's asked to kind of, move up and down, right? And so it'd be kind of the same thing where, like, if you're kind of sitting in your computer chair and then the Kool-Aid man kind of busts through your door and then asks you to do the Soldier Boy, thing, right? It's gonna take you a few choruses in order to get used to it, right? In order just to get over the shock of the Kool-Aid man jumping through your wall, right? And so for simulations, it's kind of the same thing. And so, usually we need to simulate this for more than one cycle in order for it to get used to the oscillation. Okay. And so this is definitely more of a rule of thumb thing. And so, everyone kind of has their own number for the amount of cycles that they do. But I like 4. Okay. So I like to simulate at least 4 cycles, for rigid walls in order for it to reach its its desired state. Okay. And so you can think of it, the first 3 cycles, it's using that to warm up. And then for the 4th cycle, by then it's usually good. And, then you can trust the results. Okay. And then from that 4 cycles, you would only take the results from the last one. Okay. So you kind of throw out the results from the first 3 cycles, and then you only get the results from the 4th one. Okay. Okay. And so from there, let's specify the number of time steps between restarts. And so remember, this is the number. This is how often we're going to save. Okay. And so we have to be a little bit careful with this, because since now we're solving for 4,000 time steps, we don't want to print results every single time step, right? So we have to be a little bit careful here about how often we save. Okay. And so for this one, I'm going to save every 50 time steps. Okay. And so that gives us a pretty good time resolution, but it also doesn't fill up our hard drive. Okay. All right. And so for step construction, so I'm going to do a few more modifications. And so these are all the ones that we've done before. Okay. All right. And so that's all the modifications that we've made before. Oh, one more thing. Okay. And so that's all the modifications that we've made before. Okay. And so just because we're unsteady, these don't really change that much at all. And so we can use kind of the same thing. Okay. All right. And so now we're ready to mesh and to run the simulation. Okay. And so I'm just going to run the simulation here on my desktop, because this mesh is really coarse. And so I think I saw right before there's only 45,000 elements. Okay. Okay. And so this should be just fine to run on my computer, because normally, I think for all of you guys, you're running simulations in the millions, right? And so you have millions of elements. And so that you couldn't do on your desktop, but this one's only about 45,000. And so, we should be good. Okay. All right. All right, and so that's going to take a little bit of time, and so so let's see, what can we do until then? I have so much regrets. I shouldn't have done 4,000. I should have just done 1,000 for this. Okay, let's do that. Let me go ahead and save. Actually, let's see how busy the cluster is. Let me go ahead and run a simulation there. It might be at the rate it's going. It's not even 1% done. All right. So let me go ahead and load all this stuff. Okay. No, I think we're in cylinder project, right? Yes. Simulations, unsteady. right? Okay, so we have to load in geombc.dat. Right, so look how quickly these load in because this mesh is so coarse, right? And so normally you don't want to do this, you know, because it's you know, it's used. This is probably too small to run on the cluster, but it's okay. I'm an admin, so I know what I'm doing. Okay. All right, and so we're going to run here, 24 cores. Let me bump this up a little bit, so I'm going to do 48. Okay. All right, and so we'll go save and launch. Let me stop this actually. Let me go ahead and move this again. All right, so let me change this a little bit, right? And so instead of 4,000, let me set this to 1,000. Okay. And then I'm going to relax some of these tolerances a little bit just so that they run a little bit faster. Okay, so go ahead and create these data files. Let me just double check that the changes went through. Okay, great. All right, so now let's go ahead and run the simulation. All right, now we're rolling. Yeah, so you can. So if you're running the simulation on your desktop, you know, you can check in the bottom left right here for how the simulation is going. Okay. And in fact, let me do this. Let me navigate to that file, to that folder in Ubuntu, and we can view the simulation as it's going. Where is this actually? Let me see. Dropbox. Got it. Okay. All right, and so we're here. And so if you want to see how things are going, you just do this. It does, but you can't do this with the GUI, right? And so what I'm doing basically here is I navigate to this folder, and now I'm monitoring the simulation results here. Okay. Okay. And so I think that'll still take a little bit of time to complete. And so let's talk about deformable wall simulation, because I think that's the part that's actually really cool, right? Okay. And so you know, if we go back to our normal simulation parameters here, you know, one part that we've always kind of glazed over here is the wall properties, right? And so, you know, everything we've done up to this point has been using rigid walls, okay? And so for rigid walls, you know, we basically assume that the walls are, you know, made of iron or something like that, right? And they don't move, right? But we know, you know, very well in this class that that's not realistic, okay? And so in the cardiovascular system, we know that the vessel walls are flexible, right? Because that's what's going to allow us to have wave propagation. Okay, and so by running a rigid wall simulation, we're kind of making a big, big assumption here, or big, approximation by not accounting for that. Okay? And so SimVascular does allow you to run with deformable walls. Okay, and in fact, it has 2 different modes for you to run in. Okay, but running a deformable wall simulation takes a little bit more. A little bit extra stuff that we never did before. And so let's go ahead and start a job from scratch, and I'll show you how this is done. Okay, and so let's go ahead and create a simulation job. Okay, I'm going to call this deformable tutorial. Okay. All right, and so here, we're going to be, forming our deformable. Or we're going to learn how to do our deformable wall simulation. Okay. All right, and so the first thing we have to do is we actually have to utilize this first tab here for basic parameters, okay? And in particular, we have to specify here something for the IC file, right? And so the IC here stands for initial condition, okay? And so that's, what that's going to do is it's going to provide an initialization for the velocity and the pressure field inside the vessel, okay? And so normally, we didn't use this for our rigid wall simulation. And so for a rigid wall simulation, we basically assumed that all the velocities and all the pressures inside our model, initially they start at 0, right? And so you're starting from 0 velocity, 0 pressure, and so basically completely at rest. Okay. And so the thing with deformable wall simulations, deformable wall, you're kind of getting into this realm of computational techniques called multiphysics, right? And so what that means is that you're simulating multiple different types of physics or different types of equations at the same time. Okay. So rigid wall is really nice because the only equation that you have to solve there is Navier-Stokes, right? And so that's the equations for fluid flow. And so if you have deformable wall, suddenly you add this kind of structural mechanics component in there, because not only do you have to solve for the fluid inside your blood vessels, but you also have to simulate the structural response of the wall in response to the fluids. Okay, and so you have this kind of coupling in between, the fluid mechanics solver and also a solid mechanics solver at the same time. Okay, and so I won't get into the details for all the multi-physics stuff because that stuff gets really crazy. But just know that it's not kind of a simple matter of just adding one physics to the other one. It's not just an additive process, and so it's actually a very, very complicated thing. And so, it's actually quite a bit more work. And it's actually the simulations themselves are even, even after you write the code, the simulations themselves are usually a lot more difficult to run as well. Okay. And so, one of the things that makes deformable wall difficult is that you can't start from a state where you are at 0 pressure and 0 velocity, right? And so you need to actually start the simulation out with some realistic values of pressure and velocity on the inside. Because if you don't, then what's going to happen is like imagine you're starting a simulation from 0 pressure, right? And as we just kind of learned that if you have 0 pressure on the inside, the vessel is just going to collapse on itself, right? And so you have 0 pressure, it's going to kind of suck the walls on the inside, and the whole thing is just going to blow up, and you're going to be sad, and you're wondering why you did this. Okay. And so we need to start from a pressure value on the inside that's actually non-zero, okay? And the way that we obtain this is that we actually first run a rigid wall simulation, okay? And so the starting point and so before you run any deformable wall simulation, your starting point is actually going to be to first run a rigid wall simulation, okay? And then what you're going to do is that you're going to take the results of your rigid wall simulation and then apply that as an initial condition for your deformable wall simulation, okay? Because what do we get from the rigid wall? And so from the rigid wall simulation, we get things like, we get values of like pressure and velocity everywhere, right? And so they may not be accurate in terms of deformable wall, right? Because the fact that the wall is deforming is going to change those results. But at least it's a starting point, right? And so at least it's a much better starting point than just 0 everywhere, okay? And so to run a deformable wall, the first thing you have to load in here is this IC file, okay? And I think the best way to load it in is to just double click here, okay? And then what you actually need to load is actually your restart file from a previous rigid simulation, okay? And so here, let me go to steady, okay? Right, and so this is a simulation that I ran a long time ago, okay? And so what you need to do here is you need to take the restart file, and so you can see here the restart files for all my results, okay? And then you're just going to select the last one, okay? And so here the last one is 200, and so I'm going to select that, and then that's going to be my initial conditions, okay? Right, okay. But if you're running your simulation on the cluster, you have to be a little bit careful here, because the cluster, you know, I'm not sure if you guys have peeked into that zip file that comes back from the cluster. But what you'll see from the cluster is that, you know, those restart files, there's not just one, right? And so you actually get like dozens and dozens of them, right? And the reason for that is, you know, remember when you run your simulations on the supercomputer, you're running your simulations on multiple different processors at the same time, right? And so you're running it on, like, you know, maybe 48 or 96 processors in parallel, okay? And so the way that all those processors write results is that each individual core or each individual processor is going to write its own output file, right? And so for any given time step, so let's say that, you know, we have your, let's say, time step 100, you're going to have 96 different results for that one time step, because we have 96 processors that are running, you know, different parts of the domain at the same time. Okay, and so before you load in this initial condition file from the cluster, you have to kind of combine all of those together into one. Okay, and the way that you do that is you do convert results. Okay, and you know, if you kind of if you kind of remember from before, you know, we've kind of skipped over this option here to put the last step as restart.x.0, okay? But if you want to run a deformable wall simulation and you're post-processing your rigid wall, you need to check this one to make sure that all of your rigid results, you know, from all the different processors get combined into one restart file. And then from there, you can load that one restart file in as the initial condition, okay? All right. And so if you load in this initial condition file, it's actually going to override these two guys, and so these two don't. You can just leave them as 0, and so it's just going to overwrite them, and then all that will be good. Okay. Okay. Any questions on this so far? Let's see how this is doing. Okay, 360, not bad. Okay. All right, and so that's the initial condition file, and so that's really important for deformable wall simulation. So make sure that you specify that. Okay. For the inlet and outlet boundary conditions, you know, we're not going to do too much different, and so I'm going to assume the same things. Okay. But what's important for deformable wall is that you need to run with unsteady simulation, with unsteady conditions. Okay. And so you can, and so, you know, I guess that's kind of a lie. And so you can run it with the steady simulation. It's just that you won't see anything. It'll just be really boring, right? Because the kind of the fun thing about deformable wall is the pressure wave propagation, right? And so in order to get pressure waves, you know, you need to have the pressures in there that's changing with time, right? Because if you have a pressure that pulses, and then that pulse is going to travel down the length of your vessel, okay? But if you have a steady case, you know, you don't have any pressure pulses. Everything just stays the same, right? And so what you'll probably see is that your vessel, for a steady simulation under deformable conditions, you'll probably see your vessel inflate a little bit, and then it'll just stay there, right? And so it'll be super boring, and then nothing will really happen, okay? And so in order to actually see wave propagation and to really kind of get the benefit from deformable walls, you need to run with unsteady boundary conditions, okay? Okay. And so now we come to the big part, okay? And so now that we're running deformable wall, what we can do is we can change these rigid wall properties to deformable, okay? And you can see here there's two different versions of this, but I'm just going to run kind of the easier version first, because this is a lot easier to explain, okay? Right? And so you can see here that as soon as we change this option from rigid to deformable, you can see here that we have a lot more options available to us, okay? And so these are some additional parameters that you have to set for your deformable wall simulation, okay? Because remember what I talked about before, that, you know, when you're running deformable wall, you're running a multi-physics simulation, okay? And so you're running structural simulations right alongside your fluids, okay? And those structural simulations also need to have their material properties put in in order for you to, in order for the walls to deform. Okay. And so actually, the material properties here are relatively simple because we use a pretty simple material model. And so the only three things that you have to put in are the thickness of the wall, the elastic modulus or the Young's modulus, and the density. Okay. All right. So let's start with the thickness. And so the thickness, what that refers to is the fact that our vessel walls have some thickness associated with them, right? And so we have kind of an inner diameter and an outer diameter. And so the thickness is basically just the difference in between your outer radius and your inner radius. Okay. And so normally this would be something that you would research in the literature, and so you would search up things like how thick are the vessel walls in the aorta, or how thick are the vessel walls in your veins, right? And then you would look up the what you find and put that number in here. Okay. The difficult thing is that it's one thing to say what the average thickness is for for the entire population, but there's a ton of variability in between individual people. Okay, and so it's hard to specify a thickness value that that works for everyone because everyone's different. Okay, and so usually what I do for the thickness is I specify it to be 10% of the vessel radius. Okay, and so whatever the vessel radius is, you just set it to be 10% of that. Okay, and so the question is, how do you find what that radius is, right? And so the way that you find the radius of your vessel, in here it'll be exact because I just use circles, but for you guys probably it'll be approximate because you don't have a nice circular shape. Okay, but what I do is you can't see it here because my simulation is running. What you do is you go to the modeling tab of your of your Simvascular project, and you highlight over the inlet and the outlet, or whichever vessel you think is the most characteristic for your case. Well, actually, it does show it. Right, and then in the bottom left, I'm not sure if you guys are seeing this, but in the bottom left, you can see that as soon as I click it, it's showing me the area of these faces, right? And so these two areas are actually identical because because I'm just doing a tube. Okay, and you can see that the area is equal to 12.5405. Okay, and that's in centimeters squared, right? And so that's 12.5405. Okay, and so I put that number in my calculator. Okay, and then the way that I obtain the radius from this is I just assume that our vessel is a perfect circle, and I set this equal to the area. And so in order to solve for radius, what you do is you take your area, you divide it by pi. Okay, and then what you do from there is you take the square root. Okay, because remember the area of a circle is pi r squared. And so in order to solve for that radius, you take the area, you divide it by pi, and then you take the square root of the whole thing. Okay. And so in this case, I have a radius of about 2. Okay. And then what we're going to do from the radius is we're going to take 10% of that. Okay. And then so in this case, 10% of 2 centimeters is going to be 0.2. Right. And so let's go back to our tutorial here, and let's set a thickness of 0.2 centimeters. Okay. And so for you guys, the thickness is going to be different because you're going to be working with different vessels. But this is generally my rule of thumb I use when I compute thickness. Okay. Okay. So any questions on this? Okay. All right. And so that's a thickness. Okay. And now we have the elastic modulus. And so for the elastic modulus, this is basically the same as the Young's modulus for your vessel. Okay, and so just like the thickness, this is something that you'd have to look up in the literature. Okay, and unfortunately, there's no rule of thumb for this, and so the thickness we found just based on the radius of the vessel. But for the elastic modulus, that actually takes some people actually going in and measuring what the elastic modulus of tissue is. Okay, and so this one you'd have to look up. And the elastic modulus actually, depends on what area of the body that you're in. Okay, and so the elastic modulus of your aorta is going to be different than the elastic modulus of your vein, which is going to be different than the elastic modulus of like your microcirculation. Okay, and so you really need to do some research about what area of the body that you're doing, and what elastic modulus should you specify for that area. Okay. And so for this one, I forgot what I put, and so I'm going to cheat and go over here. Okay. And so I can see here that I've applied a elastic modulus of 0.4 megapascal. Okay. Okay. But the units here are important. Okay. And so the units here, just like all units, are going to be in dyne per centimeter square. Okay. And so, you need to make sure that you put in the right units. Okay. And so for this case, I have a Young's modulus of 0.4 megapascal. Okay. And so if I want to convert this to dyne per centimeter square, I can just trust Google. Okay. And I can see here that 0.4 megapascal is equal to 4 times 10 to the 6 dyne per centimeter square. Okay. Right. And so I think 0.4 megapascal, I think that's pretty close to the aortic Young's modulus, but I'm not sure. And so it's been a while since I've really looked at all the numbers. But I think if you're in that ballpark of like 0.4 megapascal to like 1 megapascal, that's usually where a lot of blood vessels tend to be. Okay. Okay. And so now we have the density. Okay. And so for the density, we're going to put the density of blood vessel walls. Okay. And luckily for us, the density for blood vessels walls is pretty similar to the density of water. Okay. Because a lot of our our chemical composition is water. Okay. And so putting a density of 1 grams per centimeter cubed, that works for that. Okay. And then finally, we have to input an approximate pressure in here as well. Okay. And so this is something that's going to help the kind of the initial deformation field of the wall. Okay. And so for this, you can just put in whatever average pressure that you obtain from your steady simulation. Okay. And so in this case, I have a pressure of about 133,300 dyne per centimeter square. Okay. And so remember, the units for these are really important. Okay. And then we have the Poisson's ratio and the shear constant. Those you can leave alone. So those are actually fine for this. Okay. Okay. So any questions on this? Okay. And so we're about 70% complete with the unsteady simulation, and so we're trucking right along. Okay. All right. Time steps. Okay, and so here, so the same rules apply for unsteady simulation. And so we want to make sure that we specify enough time steps in order to simulate the number of cycles that we want. Okay. And the thing with deformable wall simulations is that you're going to need more cycles in order to reach the desired results. Okay. Because deformable wall simulations are naturally just a little bit more finicky and a little bit more unstable than rigid wall simulations. Okay. And so for a rigid wall, I told you to do 4 cycles. Okay. But for deformable walls, the number of cycles that I like are usually at least 5. But if I can swing it, I'll do 6, because six is usually a good amount of cycles. And then by the 6th cycle, then everything there has kind of died out. Okay. All right. And so let's go ahead and specify this to be 50 time steps before in between restarts. Okay. So let me go ahead and change this, something we changed before. Okay. Change to 0.001. I don't think I'm going to run this one, but I'll just show you how to set it up, because if our regular unsteady simulation is taking this long, then our unsteady one will take even longer than that. Okay. All right. And so one other thing that we have to change here is we have to change our linear solver type. Okay. And so unfortunately, this is another thing where I don't really have enough time to go into this, because this is several different lectures to talk about linear solvers. Okay. But in essence, what you're choosing here is how the linear system of equations is solved, right? And so anytime you have a computational method, like in this case, it's finite elements, or your finite volume or finite difference, right? You're going to end up with a very large system of linear equations to solve. Okay. And usually those systems are probably like millions of rows and millions of columns. And so, they're really not practical to solve exactly. Okay. And so what computers typically do is they employ what's known as an iterative solver. Okay. And so what that means is that it's it's going to solve for kind of an approximate solution to that linear system. Okay, but there's lots of different ways to doing that. Okay, and so for our rigid simulations, we've just been using the linear solver called NS. Okay, and so NS stands for Navier-Stokes, and so NS is a linear solver that really is specialized in pure Navier-Stokes solutions. Okay. And so, our rigid simulations are exactly that. And so they're rigid wall models, just pure Navier-Stokes. Okay. And so NS works perfectly with that. Okay. But for deformable wall simulations, because we're adding this component of the structural mechanics of the wall, the NS solver is not going to really help us out a lot here. Okay. And so the linear solver that actually has performed the best is a solver known as GM-Res. Okay. And don't ask me what it stands for, because it's I think it's like general minimization of residual ES, whatever that stands for. And so it's a good method, but I just don't know what it stands for. And so typically people just call it GM-Res, and people usually understand what you're talking about. Yep. All right, question. So essentially we have steady simulations with rigid walls, non-steady simulations with rigid walls, and non-steady with deformable walls. Yes, that's correct. Yeah. And so for your project, you're running steady simulations with rigid walls. And so at the beginning of today, I showed you how to set up non-steady simulations with rigid walls. And then finally, we're doing non-steady simulations with deformable walls. Yeah. Mm-hmm. All right. And so we set this to GM-Res, and then, just like we've done before, we're going to tighten up all these tolerances. We're going to set this to 10 right here, okay? And then from there, that's about it, right? And so, from here, we're ready to create the simulation files and run the job, okay? And for deformable wall simulations, no matter how coarse your mesh is, a lot of times it's usually best to run this on the cluster, right? So you can see here that, we're running for 6,000 time steps. And so that's not trivial, right? And so, even for my gaming laptop here, even running simulation on a mesh with 45,000 elements, it's taking a fair amount of time, right? And so, we're still only 88% complete. And so there's still a little bit of time that I have to stall for before we can view those results. Okay. So let me go ahead and save this. Okay. Right. And then I don't want to crash my computer. And so I'm going to wait for this to finish. And then I'm going to show you what happens when you create the simulation files. Okay. And then we'll go from there. Okay. All right. So are there any questions on any of this?
Is it common to model, if you wanted to model different parts of the aorta, to split that up in different models for different thicknesses? Mm-hmm. Or
yeah. No,
okay.
That's a great question. So and so what Michael was referring to is that as you go along the aorta, of course the radius of the vessel is going to change, and that changes all throughout the system too. And so it makes sense that those different sections of the aorta are going to have different thicknesses. And that's true. And so the mode that I didn't show you guys here was known as Deformable Variable. And so what this allows you to do is it allows you to actually apply different material properties to different sections of the vessel. Yeah. And so this is kind of the way that you do it. And even beyond the thickness, there's also the Young's modulus too, right? And so actually different areas of the body have different Young's moduli, right? And so this feature right here lets you apply different Young's moduli to different parts of the body as well. Yeah.
That's super useful.
Yeah. Yeah. Especially, if you're running for, there's one area of the body known as your coronary arteries. And so those are the vessels that kind of feed your cardiac muscle. And so those are actually right next to the aorta, but those have very different structural properties than the aorta, because these vessels are a lot thinner, and they tend to be a little bit stiffer than the aorta too. And so, if you're going to run simulations on the coronaries deformable wall, you need to specify, what the thickness and elastic modulus is for each of those vessels. Yeah. Mm-hmm. All right, so we're almost done.
There's a question in the chat.
Oh, question in the chat. Thank you. Oops. All right, so can I go back and explain how you obtain a value for the density again? Yeah, definitely. And so for the density, I just use a value of 1 here. And the main reason for that is because water is kind of the main chemical constituent inside blood vessel walls. And so your blood vessel walls actually have a very similar density to water. And so we usually just apply a density of 1 gram per centimeter cube here. Okay. Right, so density of water in grams per milliliter. Yep. And so density of water is just 1 grams per milliliter. And so, that's the density that we apply there. Yep. Yeah, a lot of things on this earth is made of water, and so it's convenient because if you know the properties of water, you know the properties of a lot of different things. Okay, and so our unsteady simulation is done, and so let me go ahead and show you those results, and I'll show you the initialization of the deformable wall simulation, and then we'll call it a day. Okay. All right, and so we're done with the unsteady simulation, and so now we're ready to convert the results. Okay. And so just like you've done, I want you to, you need to select the folder where all the restart files are located, okay? All right, and so where's this? Unsteady, okay? And so you can see here that this unsteady folder, this is where all the restarts are, okay? And so I'm gonna select this folder. It was already kind of selected by default, okay? And so I'm gonna say 100, or 1000, sorry. And so we're going to start at time step 0, stop at time step 1000, and our increment here as 50. Okay. And so let's go ahead and convert. All right. And so let me go ahead and save this. Oops, totally in the wrong folder. Okay. So let me go ahead and here. All right, and so it's converting the results. Some vascular says it's not responding, but I know better than that. Okay, and then it's done. All right, and so let's go ahead and go into that folder, and so we can view the results. Let's see right here. All right, so let me go ahead and load in. Let me load in the VTU file. Well, actually, I need to load the stack. Okay, and so the thing is, when you're loading in an unsteady simulation, you need to load in the entire stack of results. Okay, and so when you produce when you convert the results, you're gonna create a list of different VTU and VTP files. And so let me go ahead and load in the whole stack. Okay. Right, and so what we're viewing here is the initial conditions. Okay, and so you can see that we're starting with basically 0 pressure all throughout. Okay. And our velocity is also 0. Okay. But as soon as I go to the next time step, what you can see here is that the velocity changes. And so now we have a maximum velocity of 30. Okay. Right. And then the pressure looks like this. Right. So let me go ahead and normalize this. Okay. And so you can see here that we have a pressure drop of 2.5 times 10 to the 5th down to 2.4 times 10 to the 5th. Right. And so this is the solution after we solved it for 50 time steps, okay? And now look what happens when I move on to the next time step, right? And so the way that you move on from one time step to the next is you use this kind of play bar up here, okay? Right, and so you can see as soon as I move to the next time step, the pressure increases, right? And so now this entire model is at a much higher pressure. And so if I rescale this, you can see that the maximum pressure here goes up to 3.9 times 10 to the 5th, right? And if we check the velocity, you can see that our max velocity has gone up from 30 to 47, okay? And so what you can see here is that the solution is changing with time, right? Because we supplied an unsteady inflow, right? And so once again, we can advance forward in time. And you can see that the velocity went up to 54. And then the pressure went up to, what is this? 4.4 times 10 to the 5th, okay? These are looking a little bit scuffed because this mesh is actually pretty coarse, okay? And you can actually play this forward, okay? Right. And so, it's a little bit hard to kind of see. And so, and you can make a video too in pair view if you want. But at every time step or every time that we saved, our solutions here are changing because we have an unsteady simulation, right? And so yeah, and so with that, you're going to be able to simulate more realistic things. Okay. Oh, and I forgot, I didn't save the wall shear stress, but that's okay. Okay. And so yeah, and so that's unsteady simulations. And so if you want to run an unsteady simulation for your project, just let me know. I can send you this this flow file, right? And then you can run that for your project. Okay. But just keep in mind that unsteady simulations, they take a bit longer than steady ones. So just kind of be prepared for that. Okay. So any questions on these unsteady simulation results? Okay. Okay. All right. So let's and so last thing, let's go ahead and initialize the the deformable wall simulation, and I'll show you one extra thing that gets output. Okay. All right. And so we're here on the deformable wall, and so all of our settings are here. Okay. So we have the wall properties, we have the solver parameters, and now we're ready to create the files. Okay. And so I'm gonna go ahead and click Create Files. Okay. And what you'll notice are typically what you notice for deformable wall is that it usually takes a lot longer to run or to create the simulation files. But because this mesh is so coarse here, then it really didn't really have any issues. Okay. All right. And so let me go ahead and go to that that folder. Okay. And so this folder is called Deformable Tutorial. Okay. And so here you can see we have all of our usual simulation files. And so we have BCT, we have GeombC, we have restart, solver, numstart, inflow, all that stuff. Okay. But we have one extra file here, right? And so this file never showed up before, okay? And so this file is called displacement, and what this will show you is kind of the initial displacement of the vessel walls. Okay? So let me go ahead and double click this. Load this into pair view, okay? Right? And so here we have our cylinder. And so what this file is going to show you is kind of the initial displacement of the vessel wall, okay? All right. And so you can see here that, if we look at the displacement, we have an initial displacement of about half a centimeter, so 0.52, okay? And so this is kind of the initial inflation that we have in the vessel, okay? And so what basically happened here was that Simvascular took your results from the steady simulation, and most notably the pressure, and then it applied that pressure onto every single wall node here, okay? And then from there, it was able to compute, how much this vessel was going to inflate as a result of having that internal pressure. Okay, and you can see here that the inflation is about half a centimeter. Okay, and so if you want to view visually, how the vessel is actually deforming, you can actually do that using this filter inside ParaView. Okay, and so you can see that we have a filter here called Warp by Vector. Okay, and so what this is going to do is it's going to warp your model according to a vector quantity. And so our vector quantity here is displacement. And so let me go ahead and hit apply. Okay. And let me color this again by displacement. Okay. And so you can see here that our vessel is inflated a little bit, right? Okay. And so it kind of looks like it kind of looks like what I feel like after I go to Korean barbecue. And so I just feel really stuffed, right? And so we kind of compare this model to the base one, right? You can see here that the model is inflating, right? And that's a result of the deformable wall, right? And so because of the deformable wall, we have this inflation of the vessel wall, and it can now kind of flexibly move according to how the pressure changes inside the vessel, okay? And actually, this is the exact result that you would get if you ran a steady simulation with a deformable wall model. And so all that's going to happen is that your model is going to inflate, and then it's just going to stay like this. And so that's kind of super boring, okay? Because what you really want is that, what you really want is for pressure pulses, to travel along the length of this vessel, right? And so you want kind of one part of the vessel deforming more, and then other parts of the vessel deforming less, okay? And you actually be able to visually see, what the pressure pulse looks like. Yeah. Jumps up call's good. I've been there before. Yeah. And actually, I do have an animation I can show you for what it looks like. And so let me go up did not want to do that. Remove from quick access. Okay. Okay, and so I actually do have a video or an animation of it. And so I think it was from last year, from 417. So let me do this. Right. And so you know, actually viewing it in real time, it actually looks really cool. And so this is a research talk I gave last year, but I think here we go. And so this is kind of what it looks like in real time. And so it kind of goes a little bit fast, but what you can see here is that, you know, once the thing pulses, you can see that it's there's the top here kind of pulses a little bit sooner than the rest. So you can see that pulse kind of travel down the tree, and like all the wiggles that you see here are those waves actually being reflected, then traveling back up, right? And so, you know, this is kind of the result of you know, what you can get from a deformable wall simulation. Yeah, it's vibing, yeah. And so this is a little bit exaggerated, and so I kind of emphasize the displacement here. So normally it doesn't pulse this much, and so this is, I think this is actually like 2 or 3x what it actually is. But you know, this kind of gives you an idea, right? Because once you have this deformable wall inside your simulation, now you can actually model this pulse wave propagation, right? And so you can, you know, besides the vibe and stuff, you know, you can actually see the pulse wave go down, reflect, and go kind of reflect back and forth. And so this is you know, one of the really cool things that you can do with CFD. Yeah. All right. And so any final questions on any of this? All right. Okay, and so that's all I had planned for today. And so, you know, I want to take you know, just a bit of time at the end today just to say thank you to you guys for a great semester. And so, you know, you guys were literally my guinea pigs for this class. And so, you know, I want to thank you guys for kind of you know, toughing this out with me, because, you know, whenever you teach a new class, you know, things always, you know, never go according to plan. And so actually, if you look at my initial plan for this class, we actually took a very different path through this class than what I had originally planned. But that's okay. You know, I think a lot of the changes I made, you know, hopefully worked out good. But thank you guys for being patient with me. You know, thank you for all your enthusiasm. Thank you for all your hard work. You know, it really makes teaching special, right? And so, you know, teaching, you know, I think, you know, for me, you know, teaching is something that, you know, I think, you know, relative to what I think a lot of things can be a lot of hard work, but, you know, but seeing you guys kind of work really hard and really learn a lot of this stuff and really just show so much passion and enthusiasm, you know, that's what really makes this job worth it. And so, you know, I just want to say thank you guys for everything you put in this class. You know, I know a lot of you guys are seniors, so a lot of you guys are graduating. So I just want to say congratulations. You guys picked a hell of a time to graduate during a pandemic and everything. So, you know, I just want to say that I'm really proud of you guys. You know, I have just the utmost respect for you, utmost love, and, you know, just wish you all the best, right? And, you know, in the future, if there's anything that I can do to be a resource for you guys, you know, to write you recommendation letters or to, you know, help you debug something in the code, if you want to use some vascular later and you're having issues, right, then, you know, you guys will always have my email. I don't plan on changing my email anytime soon. So please, you know, don't be a stranger. Just reach out, and, you know, I'm always going to be here for you guys. So thank you guys again, you know, for being part of this this experiment that I had for this class, and, you know, have a great summer, and I'll see you around. Right? How'd you guys do? You guys did great. You guys did really, really well. Yeah, I'm really happy. Yeah, I'm happy to be a reference for you guys. Definitely put me down. Yeah. Thanks, guys.
Professor?
Yep.
First off,